Welcome to a journey into the applications of machine learning. In this session, we'll explore computational learning theory and probably approximately correct or PAC learning. Get ready to dive into the theoretical foundations that underpin machine learning algorithms. Let's start by understanding computational learning theory. It is a mathematical framework that is used to analyze the capabilities and limitations of machine learning algorithms. Computational learning theory helps us answer fundamental questions about learning, such as how much data is needed to learn effectively, and how well a model will generalize to unseen data. Two key aspects of computational learning theory are sample complexity analysis and generalization bounds. Now, let's focus on the PAC, that is, probably approximately correct learning framework. PAC learning is a model that provides probabilistic guarantees on the performance of an algorithm. In other words, it quantifies the likelihood that a learning algorithm will produce a hypothesis that is approximately correct. The core idea is represented by this formula: P open bracket error of H close bracket is less than or equal to epsilon is greater than or equal to 1 minus delta. This means that the probability that the error of our hypothesis, H, is less than or equal to a specified error tolerance epsilon is greater than or equal to 1 minus delta, where delta represents our confidence level. This formula provides a way to formally express the notion of PAC learnability. Let's understand the parameters of PAC learning. The first important parameter is epsilon, denoted by the symbol epsilon. Epsilon represents the accuracy parameter, which defines the maximum acceptable error rate for our learning algorithm. In other words, it specifies how close we want our hypothesis to be to the true concept we're trying to learn. The next important parameter is delta, denoted by the symbol delta. Delta represents the confidence parameter, which quantifies our tolerance for failure. It specifies the probability that our learning algorithm will fail to produce a hypothesis that meets our accuracy requirements. Sample complexity refers to the number of training examples needed to achieve probably approximately correct, that is, PAC learning guarantees. In other words, it tells us how much data our learning algorithm needs to see in order to learn effectively with high probability. The sample complexity, M, can be calculated using the following formula. M is greater than or equal to 1 divided by epsilon, multiplied by the natural log of the cardinality of H divided by delta, where epsilon is the accuracy parameter, delta is the confidence parameter, and cardinality of H represents the size of the hypothesis space. The VC Vapnik-Chervonenkis dimension is the maximum number of points that can be shattered by a hypothesis class. In simpler terms, it measures the complexity or capacity of a hypothesis class to fit different data sets. It provides a way to quantify how expressive a model is, and how well it can generalize to unseen data. The sample complexity bound in terms of VC dimension can be expressed as follows. M is greater than or equal to O of D divided by epsilon, multiplied by the natural log of 1 divided by delta, where M is the sample complexity, D is the VC dimension, epsilon is the accuracy parameter, and delta is the confidence parameter. Computational learning theory and PAC learning have numerous real-world applications across various domains. These are used in algorithm design, where these provide theoretical guarantees for learning algorithms, ensuring they perform reliably and efficiently. These are also used in neural networks, where these help establish generalization bounds and enable capacity control, leading to more robust and accurate models. Let's take a look at a simple Python implementation for calculating sample complexity. First, we define a function called sample complexity that takes 3 arguments: epsilon, delta, and VC dimension. Then we import the math module to use mathematical functions like natural logarithm and ceiling. Finally, we return the calculated sample complexity using the formula discussed earlier. This function provides a practical way to estimate the amount of training data needed to achieve desired levels of accuracy and confidence in our learning algorithms. There are 2 key benefits of computational learning theory and PAC learning. First, these provide practical guidance in determining the minimum training data requirements for machine learning algorithms. By understanding the sample complexity bounds, we can estimate how much data is needed to achieve desired levels of accuracy and confidence. Next, these provide a rigorous mathematical framework for analyzing the performance of learning algorithms. In conclusion, PAC Learning provides essential theoretical foundations for understanding machine learning algorithms and their performance guarantees. By leveraging the concepts and tools from computational learning theory, we can design more robust, reliable, and efficient machine learning systems. Thank you. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.